In the last video, we took a look at how to find critical numbers for different functions. Remember, those just gave us potential candidates for mins and maxes. But we kind of still have two open questions as of right now. First off would be, how do I know if those potential candidates actually correspond to mins or maxes on a graph? And also, how do I know if there are ever going to be absolute mins or absolute maxes on the graph of a function? Well, to help try to answer the latter of those two questions, let's take a look at what I have posed here. Is it possible to draw the picture of a graph, notice, of a continuous function? So remember, I'm going to have to imagine drawing this without picking up the pen or pencil. On a closed interval, let's say from -1 to 7, I'm going to go ahead and start to sketch this out here. So let's suppose -1 is right here and 7 is there, which does not have an absolute maximum or does not have an absolute minimum value. Well, we can try to play around with this for a little bit. I have to draw a continuous function. So let's see. If I was to go ahead and draw some continuous function, maybe I do something like this. Does this graph have an absolute minimum or an absolute maximum? This is the question, right? Let's see. Well, I could definitely say there's a lowest y value on here, and I can't really tell right now which one of these sides seems to be higher, but there does seem to be a highest y value here as well. So this right now doesn't seem like a good type of function here. It's continuous, but I'm curious if I can draw one that doesn't have an absolute max or doesn't have an absolute min. It's okay if I have one of those, but just not both. Well, maybe we could try something else. Like maybe I could do something like this. Like I go really high and then like that, right? That's a continuous function. But I'm still going to have a highest point up here, and I'm still going to have a lowest point down there. What's kind of interesting here is that it seems like this would be really difficult to do. So I'll say this seems difficult to do if the function has to be continuous, right? Because no matter how high I end up going, I'm always going to have to kind of eventually maybe come back down. Even if I was again to maybe draw a picture that looked something like this, right, and just go all the way over, then this is the highest point and that's the lowest point. It seems like there's no good way for me to get around this. So maybe this isn't possible to do. And what's interesting is that we can actually summarize an answer to this question in the following extremely important theorem, pun not intended. This theorem is known as the extreme value theorem. And here's what it says. Let's read it carefully. If I have a function and it's continuous, okay, so like the functions we were drawing, I got to draw it on a closed interval. So I got to start at -1, go to 7. Then automatically, so if you ever do this, a continuous function on a closed interval, you sketch it out, then that function attains, it acquires an absolute maximum value, f of c. So there's some x value where it hits a max. And it also gets an absolute minimum value, f of d. So that's just some other value. So there are some values, some x values, c and d, inside the interval where the minimum and maximum, the absolute min and the absolute max, will be hit. So the extreme value theorem is guaranteeing us that if we draw this type of a function, we will have an absolute min or an absolute max. So this is kind of interesting. But we could start to ask a couple questions here, like, wait a minute. Why does the extreme value theorem not work on an open interval? Why is it specifying that I have to go from A to B but not have an open interval? Well, we can really quickly take a look at why this would pose a problem. Let's suppose I was working from -1 to 7 again, but an open interval, which essentially means I could allow myself to have holes at the endpoints. Well, let's just think about a really simple example like this. I could now ask the question, what is going to be the largest y value on this graph? Well, let's say that this hole occurs up here at the value of 2. First, I could ask, does this blue graph ever get to the y value of 2? And the answer should be no, because remember, the whole occurs at 2, and the blue line is kind of only going up to 2. So if the function never hits 2, then I could start to ask, well, then what's the biggest value? And someone might go, well, if you can't hit 2, then 1.9 is the biggest, right? And the function clearly gets up to 1.9 because it goes all the way up to 2 and then stops. But if the function hits 1.9, then someone might say, wait, that's not the biggest value, Kyle, because 1.99 would be the biggest, right? It's still smaller than 2, and it's bigger than 1.9, and it's definitely something that my blue function hits. But then someone could go, wait a minute, that's not the biggest value. What about 1.999? That's the biggest value. And you could start to imagine this conversation going on forever, where someone just constantly beats out the next person by adding on another 9. And I can do the same thing in the direction for the minimum. In this case, if I have an open interval, there does not have to be a maximum nor a minimum. You could also see here, though, an additional question. Why would the extreme value theorem not hold if our function was not continuous, right? Why do we have to require that our function is continuous? Well, to see why this would be the case, let's consider a function, again, let's say going from -1 over to 7, but if it's not continuous, then maybe I would have a picture that looks like this, with a graph that goes up forever, and maybe a graph that goes down forever, right? If the function's not connected, then I could have things like a function that goes all the way up to infinity and all the way down to -infinity. So again, the extreme value theorem does not say that if your function's discontinuous and on an open interval, then you can't hit a max or min. That's not true. It's just saying, if you don't meet these conditions, I can't guarantee you of the results. And so we must, in order to guarantee the results, have a continuous function on a closed interval. And so we'll talk about in the videos to come how exactly we can use this to find where minimum and maximums are actually going to be on the graphs of our functions.